Yes, so now screen is in presentation. So let's begin uh, with the discussion of today's class. And today is week 7 of the course Multiphase Microfluidics. That is taken by Professor Raghvendra Gupta from IIT Guwahati, and this is a Swayam. The course is at Swayam portal NPTEL course, and in this particular week of the course, we have learned or the discussion have been done about the flow boiling in the microfluidic channels or micro channels, and at the same time, you have been taught about the flow measurement and techniques in these microfluidic channels, and then this another one is the particle image velocimetry, or sometimes it is called micro MPIV or microparticle image velocimetry. So how these last two lectures will be more somewhat more helpful in the experimental context, like what are the things you need in order to get the accurate measurement or the accurate imaging of the flow which is happening inside the microfluidic channel. uh, and the first lecture is about the theoretical and the conceptual aspects, what actually happens so inside the micro channel where the boiling is happening with the fluid whatever is flowing, and right, what are the different flow regimes, and what are the literature is available around that, and what is still gap and that need to be addressed. So with this we are starting uh, week 7 week 7 of the course. The course is multiphase microfluidics. Okay, so the course is multiphase microfluidics. Multiphase microfluidics. Okay, now the first question that I want you to start with is about this. Let me just tell you. Yes. So the question is, question one is, in which regime or in which flow regime the wall flux increases with the with increase increase in degree of superheat. Degree of superheat. Okay, and the options are boiling regime, Multiphase, film boiling design, nuclear boiling design, or design. None of these. So you solve this question, and another question that I just write. This is somewhat theoretical question. Explain how microscope works. So this is actually uh, the part of course where you had flow measurement techniques. There you have been taught about the microscopes, and especially in that uh, the the different techniques in the microscope like co-fluorescence, fluorescence, and the bright field imaging, and also how temperature, concentration, or the flow uh, fraction has been evaluated, or the images have been taken. So there are different types of camera. About that we will be having some questions on the camera also, but the thing is, what is the basic principle of working a microscope? So we will be looking at. So I will be actually telling you through the animation of the microscope. We will be taking some help of some videos, and we will be anyway acknowledging those which is available on the resource line. So you just go through this question. In which regime the wall flux increases with increase in the degree of superheat? The option is boiling regime, film boiling regime, and nuclear boiling regime. And that was the one question. And apart from that, we will be having some more questions. So, this particular question, the answer to this question is was the answer to this question is the film boiling regime. If you remember, this is the film boiling regime where the wall flux increases with the increase in the degree of superheat, and that was the last stage of the boiling curve. If you see, where with the superheat, actually the increment in the boiling was happening, and now you explain the next question, which is explain how microscope work. So in microscope specifically, we use it for the fluid dynamical systems, and how microscope works. So me just see some. Yes, I'm still in the call. So, so we will be taking help of two videos. So one is the uh, fluorescence microscope. So the question here we are having actually the two question. Okay. So okay. So I have to just take it in some different way so that things will be visible. So first one is the microscope working, and then we will be going on other thing. So so we will be going through this. Let's see how we will be going through.
Trending.
So this particular lecture, and then this yes, this is the video we will be going through. Microscope working animation, and this, yes, this is here now. Just let me take it and increase the size of it. If I can increase the size of it. Yes. Yes, so this is that video, and I would like to mm, Amandeep Singh. Uh, Amandeep Singh. This is a channel, uh, which is Amandeep Singh's channel, and let me just feel. Yes. Yes, so no problem now. Microscope working in animation, and this is from Amandeep's channel. So we are going to look at this, and we will see how the microscope works. Okay, so let me just take it here so that you actually look at the things in a more easy way. Rather, yes. Let me just have some sound. I think sound is not working.
Besto, built on trust. Live. Live. A practical introduction with projects and activities. Microscopes, parts and their uses. This to your eyes, through which you look. It contains the ocular lens, which makes the image produced by the objective's lenses larger. An eyepiece may be labeled with its magnification or power, for example, 5x or 10x, meaning it enlarges 5 times or 10 times. B. The body tube holds the eyepiece in position over the revolving nosepiece and the objectives. The body tube may be straight up and down or slanted. C. The arm is the curved metal piece that holds the body tube in place over the stage and the base. D.
These are parts of
The revolving nose piece holds the objectives and allows you to change objectives while looking at a slide or sample. E. The objectives are the parts at the bottom of the body tube closest to the sample you are examining. Each objective has a lens and a tube-like holder, the mount. The longer mounts hold the stronger lenses, the high-power lenses. The shorter mounts hold the weaker lenses, the low-power lenses. Like the eyepieces, objectives also come in various powers. Microscope has several objectives, for example, 4x or πx, 40x or 45x, and 100x. Some microscopes only have one or two objectives. F. The stage is the flat surface on which you put your slides or samples. G. The stage clips holds the slide in plate on the stage. H. Beneath the stage in all the Besto microscope have a condenser having standard diameter of 39.5 mm, which collects and concentrates the light before it passes through the sample. I. The iris diaphragm is used to control the diameter of the cone angle of the light transmitted onto the specimen. J. The coarse adjustment knob is the large knob used to adjust the position of the body tube, allowing you to quickly bring your sample slide into view. K. The fine adjustment knob is the small knob used to change the position of the body tube by making small adjustments to the focus of your sample. Almost all of our Besto microscopes have both coarse and fine adjustment knobs, but some have only one knob. L. The mirror, located beneath the stage diaphragm, increases the amount of light shining through your sample or slide. Sometimes we use lamp plugged into an electrical outlet instead of mirror or reflector. M. The base of the microscope is the heavy bottom part. It supports all the other parts of the microscope. N. Substage adjustment knob is used to move condenser up and down, bringing it into focus. You're probably anxious to get started using your microscope. Before you use your microscope, you need to know how to set it up properly. This video contains instruction for you to follow. You should come back to here each time to use your microscope until you know the instructions by heart as well as the microscope.
So you look at the
Step
the
1.
instruction how.
Remove the Besto microscope from its box or cover.
Okay.
Always
Okay.
pick up your microscope
So
is by
now
the reflector. Here's a helpful hint for you. Never use your microscope in direct sunlight, as the reflected light
will be
could
there.
damage your eyes.
So that is the one key.
Step 6. Light points towards the mirrors and use the plate. When the specimen slide comes into focus, it will become sharp and clear.
So you have to just
At
put the,
step 2, bring the slide or sample into view.
here is the
If you go too far, simply begin again at step 2. Step 8. When the specimen slide comes into focus, it will become sharp and clear. Step 9. To use the high power objectives, turn the revolving nose piece so you should close it under. Model Besto 10 have a special type of lens called an oil immersion lens, 100x.
yes.
This lens is used by placing a drop of oil, cedarwood oil,
And it
on the
will
top
test
of
the-
the cover slip and adjusting the position of the front lens of the objective so that it is touching the oil drop. The oil bends the light more than the air wound, so more light can enter the microscope. Oil immersion lenses make it easier to see samples because they increase the amount of light going through the sample or slide and microscope and into your eye. Convert your simple microscope into LED illumination microscope with LED light source. Our Besto LED light source illuminators.
Okay, so that was it for this particular section, and now I hope that you have got some glimpse of the the microscope. Now, what I want you to do is uh, just just some question and talk about fluorescent microscope. Okay, so there will be another question which is actually first we can look at the things that has been dealt in detail. So only there are few parts in the microscope that are very necessary. So especially we are here discussing about the light microscope. So in the light microscopes, there could be two possibilities. One is like it is a inverted or upright. So this can be inverted, inverted light microscope, or this could be upright light microscope. Okay. So there could be two choices. So both will be functioning in incidence and transmitted mode. Incidence and transmitted mode. Here also you will be having incidence and transmitted mode. Okay. Another one is upright one. Incidence and transmitted mode. Okay. So basically, which microscope has will be chosen. It depends on the requirement. Like most of the biological samples are biological analysis, which is happening in the 96 well plate or like some cubed kind of arrangement having separation between the objective and the sample is of just one glass sleeve thickness, because like most of the time these inverted light microscopes they are having very small working distance, so it is very difficult to place something which is having thicker base or thicker distance between the content that has to be looked at and the microscope objective. So that's why people go for the upright microscope, upright light microscope. Here, there is relatively higher distance between the the uh, between the sample and the objective. And another thing is like you place your sample on the slide, uh, glass slide, and then you are focusing it. So while focusing, the light is very important. So there are bars that has to be maintained, like this L, you call it like exposure, and then there is this gain and gamma. So these three factors need to be looked at carefully in order to actually understand the 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 working in real sense. So now we will be looking at this fluorescence microscope video, and this is by Meteor Duster fluorescent microscope animation. So we actually acknowledge them for this. This is an animation video. In this animation, you will be introduced to the fluorescence microscope, which is specialized type of the light microscope that is actually used for biological uh, uh, problems.
Laser as the light source. A researcher will require the use of a fluorescent microscope to
Okay,
light microscopy.
okay, so let's start.
Fluorescence microscopy is a special type of light microscopy in which the microscope uses a laser as the light source. A researcher will require the use of a fluorescent microscope to visualize autofluorescent cellular structures, fluorescent dyes or stains, or to analyze the expression, modification, and/or localization of proteins using fluorescent antibodies by a technique called immunofluorescence. In a fluorescence microscope, the light source travels in a different trajectory than in the basic light microscope that we illustrated in the microscopy experimental technique animation.
Instead of the laser light being transmitted through the sample, as in a simple bright field-based light microscope, the fluorescence microscope uses incident or reflected light. From the laser light source, the excitation laser beam travels through the filter cube, which is used to provide the appropriate wavelength of light to excite the fluorescent molecules, or fluorophores, used in the sample, then through the objective to focus the laser light on the sample. The light emitted from the sample is then reflected back through the objective and the filter cube, which filters the emitted light to the camera or eyepiece where the researcher can view the fluorescent signal. One advantage to fluorescence microscopy is that it can be used to detect and visualize multiple fluorescent molecules by simply adjusting the excitation and emission filters to detect the relevant fluorophores in a sample. Fluorescent microscopy also has many useful applications in the laboratory setting. Fluorescent dyes or stains are used to detect cellular structures. One example of a commonly used fluorescent dye is DAPI, which binds to DNA, and a second example is phalloidin, which binds to F-actin. Expression modification and/or localization of specific proteins can also be visualized using immunofluorescence, or IF. Like immunohistochemistry, IF uses multiple steps to detect specific proteins using antibodies in the sample. In IF, one of the antibody labeling steps utilizes fluorescently tagged antibodies that are detectable upon excitation using the
Okay,
appropriate wavelength of light.
so that's all for this. And now we are in a situation that we can talk about the microscope, this fluorescent microscope also we have looked at. So this, the let's take it as a question 3. Explain how fluorescence microscope works. Okay, this could also be an incident of the inverted or upright. So we are done with this. Now the next question that I want you to look at is this one. Uh, what is boiling number? Which of the following is true for boiling number? Question number 4 is, okay, question number 4 is, which of the following is true for boiling number? Boiling number. Okay. So there are some options, and in these options you have to look at and just find out which of the following is correct for boiling number. And then if you actually look at the boiling number context, then you will actually get that this boiling number is the the only factor which actually relates and which comes up in the channel boiling, and based on that different regimes have been segregated, and that segregation is actually the main thing. So uh, if you see the the options that are in hand about the uh, this boiling number are as follows. So look at these options and come up with the answer. Okay. So boiling number is option A is, this is wall heat flux. Okay. This is boiling number is equal to wall heat flux divided by mass flux multiplied by latent heat vaporization or vaporization vaporization. This is the first discussion. Another one is boiling number is directly proportional to x bubble sludge to the power 100 divided by 41. This is another aspect of this. And the C option is this is the ratio of ratio of wall heat flux and latent heat of vaporization, heat of vaporization. Okay, and the D option is a wall heat flux. This is the ratio of wall heat flux and product of latent heat of wall heat flux and mass flux. Okay, this one. So you look at this and come up with the answer to this question. So the question is, which of the following is true for the boiling number? The options are this: boiling number equals to wall heat flux divided by mass flux multiplied by latent heat of vaporization. Another one is this. And if you remember, this XBS is what? So though this XBS came up here, but you need to know what is this XBS. So this has been calculated for the bubble to sludge transition. Uh, and this transition length depends on the values like XBS equals to 0.763 RELO boiling number divided by okay. Okay, so okay, so you look at this and just come up with this. So if you remember the discussion about the boiling number, then you will be surely get the answer of this. And this has been taught in the first lecture of the week while discussion of the flow regime maps in the specifically in the flow boiling in the microfluidic channel. And just look at this and we will be discussing about the same again. So this The answer to this question is the option A, that is nothing but the ratio of wall heat flux and product of latent heat of vaporization and the mass flux. And option B is correct as per the discussion. Okay, so all the calculation about the about the transition, like transition from bubble to sludge, and at what it depends. So this from here you see that transition from bubble to sludge depends on the Weber number and the boiling number. Okay, and gas boiling number. So it is depending on that. And now these two options are incorrect because A is correct. So you just repeat. Okay, so now question 5 is the one that I am putting up. Which of the following is true for following is true for annular to post dry out, post dry out transition inside macro channel. Macro channel null flow design map well like intro boiling. You can like this. Okay, so the options are depends on depends on the ratio of density of two phases. This does not depend on ratio of density of two phases. Okay, and now what you think? Okay, so as far as I understand now, you are getting some glitches, and option C is it depends on boiling number. mentioned this is one of these. Look at this, and definitely you will. These have been is basically taught in first lecture of the week. So we will be going. We are actually taking the first lecture of the week and the second lecture of the week courses together, and then we will be going to the third lecture of the week. Okay, so look at this. So the thing is how you are actually looking at the question. So which one of the following is true for annular to post dry out transition inside micro channel? Flow design. So microchannel flow design. Well, inflow boiling. So the options are depends on the ratio of the density of the two phases. So if there are two phases, there could be liquid phase and the solid phase, gas phase. So it depends on the ratio of the two. Okay, so that is the one thing. And then another one is like ratio of the gas to liquid, you can say. So this is rho g by rho, or it doesn't depends on. So this is the function of and not the function of rho g by rho l or rho l by rho g. You can see rho g by rho l, and it depends on boiling. And so if you see the answer is this one. A A is the correct answer. Okay, not the second and not how if you remember the expressions for each, so I will be discussing each together so that entire concept comes to. So if you remember this, so we had in particular we had all the scenarios together. So here you had this bubbly to sludge transition. Okay, okay. So here bubbly to sludge transition. We have already wrote it. So this Reynolds number is based on the liquid, and then there is a boiling number, and then there were number based on gas. So the important point in this is, so one question you could write about this. Okay, uh, what is true for gas bubble to gas condition? Option A is depends on gas only. Reynolds number depends on liquid only. Reynolds number only. Reynolds number, then it depends on depends on gas only number, and it depends on liquid liquid only number. Okay, so you see how meticulously the question has been framed, and now you see in the bubble to sludge regime you are having liquid only in a non number and the gas only in a number. Okay, so that is the main thing. So the answers to the question will be is gas only in a non number. No. Liquid only in a non number and gas only in one number. Okay, and also on the boiling number as we have had discussion about this here. So now you see. Also, another question is like which of the following is true for sludge to annular transition? Which of the following is true for sludge to annular transition? So the options are depends only on liquid based annular depends on gas based Weber number. Depends on gas based number. The last one depends on boiling number. Okay, and the E option is take E option also. Depends on liquid is like that. So this is the question in hand. You look at this and come up with the solution. Solve the question. Definitely you will get some. So if you remember about this, then things will be clear to you. The expression for the transition between sludge to annular is Reynolds number to the power 1.47 and Weber number to the power minus 1.23. And if you remember, the thing is how it depends. So this Reynolds number and this Weber number, if you see, this Reynolds number is based on what? Based on liquid. Okay, so depends on liquid based Reynolds number. and the so this will not be, and this is depending on liquid waste Weber number. This is also correct, and there is no boiling number anywhere, so this is not correct. This is not correct. Okay, so A and E is the correct answer about the given question in hand. And now you see this question that we have here. The expression for the question in hand is like annular to post dry out, annular to post dry out period. The expression is 1.748 density of the gas to density of the liquid. Just erase it, and then gas to liquid 0.073, and the multiplications are 0.24 sigma 0.24 divided by G 0.48 and LH 0.04 divided by D 0.28. Okay, nice. So that's all. So you see, this is the ratio on which it is dependent on, and there is no boiling number. So this this is the one thing. Uh, so if you okay, so this so let us talk about dominant mechanism. So that is the question. So question is in flow boiling in microchannel, boiling in microchannel channel dominant mechanism. The the two proposed or suggested dominant mechanisms so there are two widely proposed, widely suggested dominant mechanism, the flow boiling inside the microchannel. So what are that? So you just thought of it. So if you remember, there have been discussion that the dominant mechanism of flow boiling in a microchannel is the reticulate boiling. Okay. Uh, and others suggested that not the nuclear boiling, but the evaporation or the convective boiling or the thin evaporation that occurs in the sludge flow, that is the dominant mechanism of the boiling. So there are two two conversations about the same. So the first one is like uh, first first suggestion is first suggestion is nucleate boiling. Nucleate boiling is the dominant mechanism of flow boiling in microchannel. Flow boiling in microchannel. Okay, flow boiling in microchannel. And this they have suggested this because as evaporation depends on the heat flux, because evaporation depends on heat flux. Heat flux. Okay. Second is second is uh, evaporation. Evaporation. Evaporation or convective boiling. Convective boiling or thin film evaporation. Thin film evaporation. So, occurs in the sludge flow. In sludge flow is dominant mechanism are boiling. Okay. So these are the two streams of the dominant mechanism. So if you remember in the conventional channel, the nuclear boiling dominates in the bubbly and the sludge flow patterns. Okay. Okay. So this is the one thing. Why? Because the enhancement in the heat transfer process arises from the evaporation of the liquid of thin liquid film underneath the bubble during its growth. Strong mixing in the bulk flow due to the bubble agitation after it leaves nucleation sites. And also, if you remember the bubble generation frequency, departure diameter and the diameter range of the active nucleation site increases with the heat flux and the pressure. So while the heat transfer increases with the heat flux and the system pressure, and also the system pressure, but is independent of the mass flux and the vapor quality. So vapor quality, you remember the mass of the gas to the mass of the gas plus the mass of the liquid. So that's the why the nuclear boiling contribution is determined based on these effect, and so it has been proposed to be the dominant uh, uh, mode of mechanism of boiling. On the other hand, in the conventional channel, this convective boiling dominates. Also, why? Because at high vapor quality and the annular flow regimes, right, mechanism similar to single phase force convection, but enhancement happens here due to the increased gas velocity and the evaporation of the liquid. This dominates when heat transfer coefficient increases with the increasing the mass flux and the vapor quality, but is independent of the heat flux. So that's why this conventionally inference says that this domination is actually this convective one dominates. So that's all about this, and there have been different questions. So let's see another question that we are going to solve now. The question is, this is the last lecture was the lecture was mostly about themes. So we will be discussing some of the context that he has told. So what theme and Consolini that again in 2010 suggested about dominant mechanism of flow boiling in microchannel. In microchannel answer is, we will see. There have been different discussions, so I want you to think about this, and then we will be looking at this. So if you remember, I will be going to this in faster mode, and the only thing is he said many things. So we will be looking at most important points. So he divided the three regimes based on the vapor quality. So the first is at low vapor quality, intermediate, intermediate, and another one is high vapor quality. So these are vapor qualities. Okay. So the in the low vapor quality, if bubble flow, there will be regimes like bubble flow, bubbly flow, regime, and the thermal transport dominated by nucleating. Thermal transport dominated by nucleate. Okay, dominated by nucleate boiling. Okay, that's the one thing. The in the intermediate, you had, so there will be passage of this passage of elongated bubble and the sludge of liquid. Elongated bubble and sludge of liquid. Okay. Then there will be heat transfer by the single phase convection in all liquids and the vapor zones, and by conduction or convection through the liquid through the thin films. Okay, so that will be, there will be that second point, heat transfer by the single phase convection in all the liquids and vapor zones, and by conduction and convection through the films. And also this is highly dependent on the bubble frequency. Depends on bubble frequency, which is what is the bubble generation frequency. Okay, and the next is, if the quality is high, then you will be essentially in the annular flow regime flows. And also the heat transfer is expected to be governed by the convection and the conduction mechanism involved in evaporation of the annular film. So conduction and the convection for annular flow heat transfer. Okay, so now if you see this, uh, you will be in a situation to tell that this dependence of the boiling heat transfer coefficient on the heat flux, uh, that is explained by the thin film evaporation process and the s- uh, cyclical heat transfer process occurring in a elongated bubble flows. So then elongated bubble frequency and the transient heat conduction process are strongly function of the heat flux. So that's the point that the question was talking about. And if you see, yes, we are still live. And if you see this, based on this, we will be having next question. And the next question is, so we will be having the next question. In flow boiling in microchannel, for, let's start with like this, for flow boiling in microchannel. Okay, the convective boiling heat transfer regime in the convective boiling heat transfer regime, the heat transfer coefficient, heat transfer coefficient is strong function of, so the options are vapor quality, If you remember, the vapor quality is mass of the vapor or gas plus mass of the vapor or gas plus, and we see if something happened. Yes, so vapor quality, and next option is mass flux, then which is a, and sometimes see the heat flux, so it's Q, and also none. Which of the following is correct? So if you remember this in the discussion, you will be in a situation to tell the answer of same. So the you just look at it. Look at this. How this convective boiling heat transfer enzyme is having its heat transfer coefficient dependence. So based on the above discussion, now you see the answer to this will be it depends on the B and C, which is mass flux and the heat flux, and this has been taught in the lecture. So you look at that, so about the convective boiling heat transfer. And now question is how vapor how vapor quality dictates flow structure inside flow boiling microchannel. Okay, so what could be the answer to this? How vapor quality? So vapor quality is the one that we have already looked at. Mass of the vapor to the mass of the vapor plus mass of the liquid. So how that actually decides the flow morphology in the microfluidic channel. So you look at this, and we will be meeting soon. So you look at this and think in terms of like how different flow morphologies are there, inside the micro channel when the boiling is happening, and there is the different zones like bubbly zone, and then the sludge bubble, then this annular so the how you will relate it to the quality value. So yes, I hope you have gone through the notes that you had during the lecture, and the main thing how you will look at the effect of vapor quality or the value of quality to the morphology is like you you actually look at this. Let me just have it anyways, so things will be much better. So let me just have it. Okay. Yes. So it's here. You just take it. Okay. Yes. So yes. Now I hope that. Oh, yes. So here you see, like when small bubbles are there, so less bubbles are there, and there is continuous medium. So definitely quality will be low here. So for the low quality means low, so x equals to 0, and x is defined as a quality, I think. So you can have symbol x also for the quality. Okay, so this for the low quality, you are having bubbly flow resin, and then uh, uh, if you move ahead, the nucleate boiling and the liquid film evaporation in the slush flow, one bubble nucleate in the liquid film. Okay, so then further increment in the quality is happening when there is a bubble and then this liquid convection in between. So this thin film evaporation, which is most contribution occurs at the tip, and that calculation has already been discussed in the class when the bubble nucleation in the liquid film or the liquid sludge is completely suppressed, then you are actually looking at this. And then the last which is actually happening if you are having very high quality is the convective evaporation in the annular flow where nucleation is fully suppressed. Okay, so that is the nucleation. There is no bubble formation, and this is the annular fluorescein. Okay, so now we are done with this question, and this was the the main thing that I was actually expecting from you to tell. And now, what are the uh, what is Thum's three-zone model? So, which of the following is correct about question? Which of the following is correct about Thum's three-zone model? Okay, so especially we are talking about the assumptions. So first is bubble generated continuously and grow downstream. No collisions. Film is stagnant. This is nuclear boiling model. Boiling model to predict heat transfer coefficient. Okay, this is convective boiling model. Constant temperature boundary condition. Constant wall temperature boundary condition. Okay, so that's the options. So if you look at the answer to this, and if I actually pinpoint you, so obviously this one is incorrect because this is constant wall heat flux, not the constant temperature. So this one is incorrect, and this is like convective boiling model. This is correct. This one is incorrect. This is correct. This is correct. So A, B, and D are correct option for the given question. So I am actually moving fast because like we are having lag time and we will be going through some more questions. So that anyway these videos will be recorded. These are recorded and these are available on the portal website. So you can go through it and you can also look at it in a way this will be kind of revision session for you, and so questions will be created from the slides which will be definitely helping you in solving the weekly assignment, and also it will be having a type of question that will help you in performing well in the final certification examination. So that's the one thing, and this let us discuss some more about uh, Thum's model. And so, if you remember, I will be actually directly telling you this rather going to through the. through the question is like Thum's three zone model. It has what the Thum has considered. If you remember, the main thing is like the zones that he has considered, and there, if you remember this Thum's three zone model, they have considered zones. So let us write the question itself. So question is three zones, three zones considered by Thum in convective boiling model. Explain. So we will be looking at that particular slide itself. So to save the time as well as have the clear understanding about the same. So let us see. Yes, it is here. So if you remember this, what it says, like there are three zones that has been considered. The three zones that has been considered. First one is saturated liquid sludge. Okay, and then there is elongated bubble which traps a liquid film. Okay, so there is a liquid sludge and there is a elongated bubble that traps the liquid film. That is the one thing. So this is there is a elongated bubble and this liquid film is trapped between the wall and the elongated bubble. There is saturated liquid sludge is there. And also here, if you see, there is something called dry patch. This one is dry patch where is no liquid film. So dry vapor zone, if dry out occurs before the arrival of next sludge. So this dry out occurs if the next sludge is coming up or approaching the zone, the dry out zone rather. Okay, so these are three zones. And if you see the bottom one, here we are clearly looking at the things like elongated bubble. Then this there are circulations definitely inside the sludge. Okay. Yes, so there are elongation that can be seen through the pictorial presentation also. So now we will be moving towards the question about the local time average heat transfer coefficient. In Thom's three zone model, local time averaged heat transfer coefficient is defined as option A is sum of heat transfer coefficient in each zone, sum of heat transfer coefficient in each zone. Okay. B is H as a function of Z T is equals to T fill H fill divided by tau C H Z T equals to P fill H fill Z tau T dry H dry function of Z anyway divided by tau H equals to T liquid slab H liquid slab is the function of Z divided by tau plus plus okay so you can write it T fill H fill T dry H dry which are the following is correct. So if you see and if you remember the option A and option D, this is the option is the correct answer. Option A and option D are correct answer. So now these are some questions that we have discussed, and there are some more questions that could be asked based on the discussion that you had in the Thom's model. And so we will be looking at the differences between CCD and CMOS. So there are cameras. If you remember the discussion question. So in the microscope, you are having different cameras. So 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 difference between difference between charged charged coupled device that is CCD camera and charge coupled device and CMOS, which is complementary metal oxide semiconductor. Complementary metal oxide semiconductor. Okay, that is CMOS. Yes, so we will be looking at these. So first is the CCD, another one is the CMOS, and this is the barrier. Okay, this is the barrier. Okay, so let us start with the CCD. So this converts light into electrical charge. Converts light into electrical charge into electrical charge. Okay, and so there will be like a rectangular channel on that. Number of these CCD arrays will be placed. Number of these CCD arrays will be placed. Okay. So this there is like pixels are charged by incoming photon and transferred through a very limited number of output nodes to be converted to the voltage buffered and sent off chip uh, as an analog signal. All the pixels capture the light and the output uniformity is high. So this will be good if there is a low signal to noise ratio. So good for low signal to noise ratio, and this is costlier than CMOS. Costlier than CMOS. So also you can see that CCD camera, which is based on the charge coupled device, and we write it CCD camera को we write it. This is based on the photoelectric effect and the based on photoelectric effect. So we can write that also based on photoelectric effect, and also the CMOS one is based on the photoelectric effect. So both are based on this photoelectric effect. So in this we have just talked that there will be array of many individual CCDs or many individual sensor element. They are arranged into a line or the rectangular area, and these elements we call them as a pixel, and these pixels are charged by the incoming photon. So the charge in this charge is transferred to the limited number of the output nodes, which is converted into the voltage, and this voltage is sent off as an analog signal to the computer. So this the speed of the CCD camera is limited by the number of outputs and through which the signal can be sent. So the frame rate that can be achieved in the CCD camera is limited. So RPS is low. Frame rate is limited. However, they have, because all the pixels capture the light intensity and the uniformity of the outcome is high, so they have low signal to noise ratio. Okay, and the picture quality that one get through the CCD camera is better. Okay, especially in the low light, CCD camera known to perform better than the CMOS. So here perform well well in CCD in low light than CMOS. Okay, this is the one thing, and the another one that we will be talking now. So so uh, uh, and also one thing that we can talk about this is is the manufacturing are the special technique and is need to be used. So they are costlier. They are costlier. Obviously, these are costlier and than the CMOS one, uh, where the metal oxide layer is there. And the CMOS one that we will be looking at now is the this like based. This is also based on photoelectric effect. We know these are high speed camera, and there are CMOS sensors. So the first one is like high speed camera. Okay, here each pixel has its own charge to voltage conversion. Okay, each pixel has its own charge to voltage conversion. Okay, that is important point. So each pixels are having their own charge to voltage conversion, and that actually ensures that how things will be going on. And the another important point is like these CMOS sensors often include digitalization circuits, like chip output digital bits will be there. So large sensor size will be there than the CCD sensor, and they can range from the 20 micron to 9 micron. Uh, and these are highly sensitive to low illumination level. Okay, so let us look at this. Mm, so in the CCD, you are having sensor size to be 9 micron, but in the CMOS, this is around 20 micron. So if you see here, sensor size is what? 9 micron. Here it is 20 micron. Okay. Also, the sensitivity of too low illumination level is high, so CCD is good. So they might perform poorly or they perform poorly when you compare with the CCD. Uh, uh, because CCD is performing well in the low light. However, they can have very high speed, thousands of frames per second, or at low pixel or at low resolution, they can even go to up to 500,000 frames per second. So the most of the high speed applications are based on the CMOS camera, and with the new development in the camera technology these days, the sensors are being developed which combine the good of both outwards, which you can use CCD camera technology for the better resolution and CMOS technology for the better or the high speed. So these camera they need to be used along with the zoom lenses or the microscope. So the simplest microscope that is used in this is the bright field microscope. So we understand that when we came to know about all these different cameras, and we have also discussed about like the this microscope, and there we had like bright field microscopy. We have discussed the simple optical microscope illumination technique where the simple illuminated from the below and observed from the above, or it can be illuminated from the top and observed from the top itself because of the reflection. There could be any arrangement based on the upright or the inverted microscope you are having, and also the contrast caused by the attenuation of the transmitted light in the dense area of the sample will be responsible in order to get the information about the same. Okay, so camera shutter time is the important parameter that takes care about the quality of image, like time for which the camera sensor is exposed to the light, and it determines the light that reaches the camera. Okay, so the speed of the camera which sufficiently short camera shutter time. So high speed of cameras there will be short shutter time. Okay. And also we have discussed about the fluorescence microscopy, and in that we have already discussed that there is obviously this simple illumination technique in the visualizing through the bright field microscopy, but there is some limitation. So the fluorescent microscopy is often used and it has number of applications, specifically with respect to the diagnostics in microchannel, or they can measure the void fraction distribution. One can measure the fluid velocity, or can measure the temperature field, or can measure the concentration field with the fluorescent microscopy. So in that there are fluorescent microscopy in this the sample is illuminated with the light which is often of the specific wavelength. So this light is monochromatic light. This can be done using a sub say X-ray, no, say xenon arc lamp or the mercury vapor lamp LEDs or laser, and this light which is incident on the sample, and this sample seeded sample means the flow. Okay, one of the phase of the flow, often the liquid phase or the continuous phase, it's seeded with the fluorescent particle or which are called fluorophores. So these fluorophores, what will happen? So these what are the fluorophores? These are the particles. Like these particles will be modified with the fluorophore property chemicals, and they absorb incident light and they emit the light. Now, when they emit the light, they emit the wavelength of the emitted light, and the energy of the emitted light is different from the energy of the incidence of the light. That is incidence, of course, the energy of this light that is emitted with the lower than the light that is incident as a result of the wavelength of the emitted light, which will be higher. So based on that, you are having different colored images. Okay. So here there are some other things like this. What are fluorophores? So some of the question that you can write. Question is like there could be some question. What is fluorophore? Fluorophore. Okay. Okay, so this is the one question. So in short, I can answer you like the fluorophores, they emit a light of the longer wavelength when the light is incident on it, and this light is collected and goes to the detector, which may be camera using a dichroic mirror and the emission filter. The illumination light, the light which was going used to illuminate the separate the from the fluorescent light. Okay, and there is something called epifluorescence microscope. This is what? This is both the light which is used for the excitation of the fluorophores and detection of the fluorescence. Both are done in the same microscope. What is that is a fluorescence microscope in which the excitation of the fluorophores and the detection of the fluorescence both are done in the same instrument. This is called epifluorescence microscope. So you can write another question is what is epifluorescence? Epifluorescence microscope. Okay. So this is the another question that could be answered, and so it is basically that the images are taken of the fluorescent particle. So based on the intensity of that fluorescent particle, or one can capture a field, and if this intensity of the emitted wavelength or the emitted light is temperature dependent, then one can also measure the temperature field. It is concentration dependent, then one can measure the concentration field. And it is not dependent on such a parameter. They then one can measure the distribution of the one phase. So what can be measured? Concentration, temperature, distribution, or the fraction, what fraction? Uh, and also based on that you can measure the concentration. So 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 here comes the particle image velocimetry. uh, so like it is often used, and this technique is also used, or epifluorescent microscope are also used for the micro PIVs, microparticle image velocimetry application, because the illumination in the micro PIVs is the volumetric illumination, unlike a general PIV or the 2D PIV where the illumination is through a light sheet. So we have discussed about that. Okay, so so that fluorescence and everything you have talked about. So so these are something, and let us have some other question about the same. Like, so I will be talking about another question. The question is, which of the following, which of the following flow measurement technique is non-intrusive. So the option A is beta tube. Option B is rotameter. Option C is potentiometer. Option D is particle image velocimetry, micro PIV, that is micro particle image velocimetry, geometry, and option D is orifice meter. B is orifice meter. So if you remember, in all these flow meters, you are actually touching the flow line through some flow. And if you do so, so this non-intrusive, you have to actually look at that in a way that you actually understand what the question is saying. So, so this non-intrusive is like you are not actually getting too close to the flow or touching the flow. Okay, so this micro PIVs here, you are actually having seeding the geometry in the system with the fluorescence uh, particles, and based on that you are looking at the things. So this micro PIV is the correct answer for the same. So some discussion about this what is particle image velocity? What is particle image velocity? So that is the question. You look at it. So there are some points about this question, and if you write that point, uh, is like this particle image velocimetry is based on the velocity of the particle flowing through the fluid, and also it requires optical access to the channel. So optical access, like channel walls or the channels should be of glass or some transparent material, so that you are actually looking at the flow pattern or the movement of the particles or the movement of the seeded particle inside the channel. So this is the one thing that has to be there. And then this is a non-invasive technique. So these 3 points are straightforward that we are going to write. Is like this is like non-invasive technique. It does not have direct contact with the thing. This is non-intrusive flow measurement. Okay, then it is based on the velocity of the particle flowing the fluid, based on velocity of particle flowing through the fluid. Okay, and the next is requires optical access to the channel. Optical access to the channel by measurement. Okay, so that is the one thing. And this movement of the particle will be can be visualized using different microscope, especially the fluorescent or epifluorescence one. So this particle image dosimetry is a optical method of visualizing flow, and this is from here you can observe the instantaneous velocity measurement and relate it to the fluid property. The fluid is seeded with the tracer particle, which for sufficient small particle are assumed to faithfully follow the flow dynamics. Also, so there will should be this. The important point is like your particle should be well behaved. Okay, so like the fluid is seated with the tracer particle, which for sufficiently small particles, will faithfully follow the flow dynamic. Also, the fluid which entrained particle is illuminated so that the particles are visible. The motion of the seeded particle is used to calculate the speed and the direction of the. So there are different techniques also: laser Doppler velocimetry and hot wire anemometer that could will be giving you the three-dimensional vector fields, pressure fields, concentration fields, and so on and so forth. So you can also look at that. So these are the typical things, uh, properties of what we have had discussion today, and this this is like this for the velocity measurement. Obviously you are having different techniques, so there is no much problem associated with that. But this is the non-invasiveness is the one thing that is very important in terms of PIP. So this here there will be like you will have whole field velocity measurement, that is high spatial resolution will be there. So like complete velocity measurements you will be having. And also through this particle image velocimetry, you need to have first the particle should be seeded and it should behave faithfully. Another one is like there should be illumination through the laser, and also the image of the flow is, is being captured at different time instances in the single frame or in the two different frames. So images are sectioned. You have to have the interrogation region where there should be small interrogation region, and also the displacement of the particle within each interrogation regions is determined by autocorrelation of the single frame or cross correlation of the two images. Okay, so that is all about this particle image velocimetry. So we can have the pictorial representation of the particle image velocimetry for your reference, so that you actually understand what has been directly we have discussed till now. So these are the arrangement. The light source is here, laser source, and this is illuminated in the 2D. And 2D illumination here, you are having flow out, particle laden flow is happening, and based on that, you are capturing, having the image optics that will have different images, and based on that, you are actually comparing the two images and the measuring the velocity of the same. So you need the tracer particle, you need a laser and the optics, you need camera, you need synchronizer, which will synchronize the the phenomena that is happening anyway with the light, the fluorescent effect of the particles, and also the the FPS frames per second. And also there are different post processing devices that will help you to post process the thing. So there are some properties of the tracer that has to be considered. So your tracer should be fully faithful. So tracer property is like uh, tracer property. So this tracer property is like it should be fluid faithful. It should behave properly. Another one is it should be non-buoyant. Almost same density as that of the fluid. Another one is like it should have fast response to the change in the fluid velocity. So fast response to the change in fluid velocity, and there should be this there should be these properties of the tracer that has to be considered by performing the PIV experimentation. So thank you so much for today's class. We have solved plenty of good questions and many questions, and also I have had created some of the questions while giving the solution of the questions that are on the desk. So thank you so much, and we will be meeting in the next class, and that's all for today's class. Thank you so much.